be just talking about 30-meter telescope project and India's contribution in building the 30-meter telescope. So my name is Ramya Sethuram. I'm project scientist at India TMT Coordination Center here at IIA. So what is the 30-meter telescope? I don't have to, this is not a new thing for any of us. So 30-meter telescope, international project with 5 countries, US, Canada, Japan, China, and India. India is partner. There are 3 primary institutes coordinating the effort from India, and those are ARIES, IAA, and IUCA. And DST is our funding agency, DST, DAE together. This is how the TMT would look when it is being built. This is rendering, new rendering from TMT project office. And the tentative construction would begin from 2025 and the operation would begin from 2035. So the first light instruments, there are 3 of them actually. So WFOS is the seeing limited optical instrument. Nefarious is the adaptive optics facility of TMT. That feeds into 2 instruments, science instruments, which are infrared imaging spectrograph and MODIS. MODIS is high resolution IR spectrograph. So the second generation instruments are HROS and IRMOS. HROS is again works in the optical high resolution spectrograph, and IRMOS is multi-object IR spectrograph. So the first light instruments, I'll just go a little bit more detail into it. Nefarious is the narrow field infrared adaptive optics system. This will provide the adaptive optics beam at a wavelength range of 0.8 to 2.4 microns. And it works in both natural guide star mode and laser guide star mode. So the beam from the Nefarious feeds into IRIS. IRIS would look something like this. It's near IR imager and IFS in the range of 0.8 to 2.4. And IRIS is a very competitive instrument. It has an imager. As you can see, the imager is 34 arc seconds on the right side over here. Apart from that, at a pixel resolution of 0.004 arc seconds, you can also get lenslet slicing IFU at 0.5 by 0.5 arc seconds with a spatial sampling of 0.004 arc seconds per pixel. So there are a few other possibilities with higher resolutions and a lower field of view with IFU possibilities with IRIS. So the WFOS is the seeing limited optical spectrometer, 0.31 to 1 micron. So this has again multiple resolutions, 1500 to 3500, and also 5000 is possible at the slit widths of 0.75 arc seconds. This is seeing limited, may work in GLAO, ground layer adaptive optics, in the upgrading phase over the next 10 years after the operation. And the field of view is 25 arc minutes square. So which means you can put up to 60 targets with 8 arc seconds slits, or the gap between, with 3 arc seconds gap between the 2 slits. So it can also give a imaging which is for the full field of view at a pixel scale of 0.05 arc seconds per pixel. So the final first generation instrument is MODIS, which is multi-object diffraction limited high resolution infrared spectrograph. It is a very small spectrograph compared to the size of other 2 instruments, and it can give a resolution of more than 100,000 with 30 centimeters per second as the velocity dispersion. It works again in the IR. So there are 2 IR instruments and 1 workhorse optical spectrometer for the first light, as first light for TMT. So there are other first decade instruments which are being planned, and I just want, there is a list, and still there are thoughts about how things have to go for GLAO and mid-IR adaptive optics systems. But I would like to bring to your notice that HROS, high resolution optical spectrograph, is being led by India. So its capability is about 100,000 and 50,000, multiple capabilities actually, 100,000 resolution, 50,000 40,000 and 20,000 through slits. And it can also give a multi-object, it can also work in a multi-object mode in a field of about 5 arc-minute with a resolution of 25,000. Again, high-resolution optical spectrograph is going to work in 0.31 to 1 micron. So the next first decade instrument would be IR-MOS, which is also very interesting. This would actually be very useful for high redshift objects because it's going to be a multi-object again in the IR 0.8 to 2.5 micron and also has multiple resolutions 2,000 to 10,000. This is where high redshift galaxies can be studied. So this is the TMT capabilities in a nutshell. If you have a seeing limited, if you are using a seeing limited instrument, it goes as D square, so it is a 14 times gain over a 8-meter class telescope. Now, if you have adaptive optics, it gives you a gain of almost 200 compared to an 8-meter class telescope. Now, the area is the diffraction from the spatial resolution. When compared to JWST, is 5 times better spatial resolution, and when compared to HST, it is 12.5 times better. So now, comparing the TMT capabilities with other ongoing surveys or on upcoming facilities, if you see that this is the faintest limit that TMT can reach. So at the 32 magnitude, you will be able to obtain Z-band imaging at a signal to noise ratio of 10 in 20 minutes. So that's the limit for TMT. If you want a H-band image that can H-band spectroscopy, signal to noise ratio of 10 at a resolution of 8,000, it is possible in 1 hour, and the optical limit will be about 26th magnitude, giving you a signal to noise ratio of 10 with a resolution of 1,500. And this is perfect for Z is equal to 1 to 2 kind of systems. So when compared to JWST and other observatories, it is TMT's capabilities, of course, much better. So continuing with the TMT's capabilities, angular resolution versus the wavelength, as you can see for the seeing limited, it is on an average monopia seeing we have taken here, and that is about 0.5 arc seconds. So with respect to the seeing limited, the performance is something like this, between 0.3 to 1 micron. Now at from IR 1 to 30 microns, TMT AO will perform really well. So which means to say that at Z is equal to 1, you will be possible to look at scales of few hundred parsecs with the TMT AO. That is one of the IRIS instruments or MODIS instruments. Coming to the core science cases, so TMT's achievable limit would be Z is equal to 20. So from 20 to 6, what is the most important science cases? Of course, the science cases, what I have chosen is extremely limited to what this TMT's capabilities are. But this is of currently what I think is the best, what TMT should aim at. And this is all the science cases which is approved in the TMT science documents. So this is all well thought about science cases. So what are the sources? What are the sources that that created the reionization era? If you think of those sources, so those sources could be truly a primordial galaxy or POP3 kind of systems, which created the reionization epoch. So if you can see this figure over here, what we have plotted, what the science case has plotted here is that if you, the UV luminosity function for Z is equal to 6 systems, Z is equal to 7 and Z is equal to 8 systems is plotted over here. And you can see that if you have a truly primordial galaxy where there are absolutely no metals, then the spectra would look something like this. The bottom plot here is the stellar, you will not have any stellar continuum, but you will have a nebular emission, something like this, filled with Lyman alpha, helium, and hydrogen recombination lines. This helium 1640 angstrom line is the most or the best tracer for POP3 and primordial galaxies. So this line, which is at 1640 angstrom at rest wavelength, will be shifted to iris wavelengths. So it is very well it is very well observed. Of course, these can be very faint. We will need a lensing galaxy in between to catch them as well. So having said that, at z is equal to 7. So there are some of these lines for galaxies already observed, and these lines can be easily observed at z is equal to 14 with TMT. So this is an interesting science case to understand what could be the ionization source in the earlier form. So coming to Lyman break galaxies. So these are these are interesting systems which the JWST has is finding out, and these can be filled in the z is equal to 3 to 7. Of course, there could be higher redshift LPGs as well, but in this redshift range, we will have more chances of seeing LPGs. So why are Lyman break galaxies important? They are actually could be high redshift counterparts of low metallicity galaxies found at z is equal to 0, like XMPs, low metal BCDs, etc. So this is particularly of interest because there could be these Lyman break galaxies could have gone through a feedback and would have lost all metals, and it would take time for it to get back all the metals and then process it into forming larger galaxies. So that problem is there. So maybe if we can connect XMPs, BCDs with the LBGs, or if we see any connection between them, we can understand how the LBGs are evolving. So for that, we will have to study z is equal to 3 to 7 LBGs. So these are some of the work which recently JWST has given. So you have to find out LBGs again through galaxy lensing in this redshift range. So again, it is dropout methods where you will not see them nor detect anything in the optical, but when you go in IR, you will start seeing them. And the SEDs of LBGs would look something like this. And using only the photometric redshift, you can find out what would have been its real photometry. Now, the sizes with these limited estimates, you can also find out what is the morphology of these galaxies, and you can find out the size luminosity relation. You can see that the size is very small for these galaxies. It is about a few hundreds of parsecs. So that is a pretty challenging thing even for JWST. Now, these things can be resolved with the TMT AO, that is basically iris, because it has a 12 milli-arc-second resolution. Now, if you have to see this with the TMT AO, that is also difficult. You will have to bin the pixels to get a 50 milli-arc-second. So with the 50 milli-arc-second, the sizes what you can resolve will be 0.15 to 0.25 kiloparsecs. So which comfortably will be able to resolve these very small galaxies with the TMT. Now, we don't just want to resolve the galaxies, we want to also see the spectrum of it and measure what's the metallicity and star formation rate and other things. If we have to do that, these could be at a HAB magnitude of 27 magnitude. So we will require a 10-hour integration, and this would give us signal-to-noise of 10. So if we are aiming to see LBGs, there are other sub-L star galaxies, also very faint galaxies. What we have till now studied with the high redshift is a very brightened universe. So there are, to understand the total galaxy formation and evolution, and also to understand how the dwarf galaxies have, whether they have really taken part in the reionization epoch. So we need to understand these sub-L star galaxies. So these could be at a magnitude of -18 to -21, sorry, at M 1600 monochromatic magnitudes. So this has to be lensed at z is equal to 3, which can be easily observed with TMT. Yeah. So that was one of the interesting science cases. Oh yeah. So coming quickly to one of the interesting science cases, or the main science case for WFOS would be to understand the baryonic structure of the universe. So that would be like we would be looking into z is equal to 1 to 6. We'll be probing into z is equal to 1 to 6. And as you can see, we will see a lot of IGM and CGM activities. We can try to understand the feeding and feedback happening, how the galaxies are growing with respect to black holes. So this is one thing. So with WFOS, 1 hour exposure gives a signal to noise of 5 at a resolution of 1500, and we can go up to a 26.5 magnitude. And if you want to study about 12,000 or 120,000 systems, then it will require about 1,000 hours of TMT WFOS time. And similarly, if you have to do an IGM study in the redshift range of 1.6 to 3.5, we'll reach about 24.5 magnitude in 5 hours of integration with a signal to noise of 35. So these things will help us to map the metallicity, star formation rate, stellar mass of these galaxies. Also understand the metal content of these galaxies. If we have to do that, right now we have to do a spectral stack for several of these galaxies at z is equal to 2. That is what they have done here, and you can see a lot of metal lines. So these will be helpful to understand. So the peak of galaxy assembly is again between z is equal to 1 to 6. This is from Malo and Dickinson 2014. So you know that the star formation peaked somewhere between 1 and 2, or more specifically towards 2, and the black hole accretion activity also peaked somewhere between 1 and 2. So these two are connected. So not only this, how to understand galaxy assembly, assembly of galaxies from z is equal to high redshift to a low redshift. So IR-MOS would help us to do this with, for example, if you have a field of this kind, IR-MOS could be able to point to about 10 to 15 of these galaxies which are just forming. And this is how the spectrum would look like. So with TMT, you can understand the peak of galaxy assembly between z is equal to 1 to 6 by using both WFOS and IRIS. So WFOS, the rest wavelength from 1200 will be shifted to the optical regime, so which WFOS will be able to catch, and the IRIS will be able to observe the rest optical wavelengths, optical spectrum of these high redshift systems. Again, to understand the growth of stellar mass and black holes. So at z is equal to 1, if we are able to obtain a spatially resolved data, we can understand how the bars and disks are forming. This is taken from Sheikh et al. 2008, who say that the bar fraction reduces from lower redshift to higher redshift. So if you either measure it visually or if you measure it with the other parameters like ellipticity and position angle, you will see that the bar fraction, which was almost as high as 70% in the local universe, you wouldn't see them at high redshift universe. The systems with bars would reduce completely to 20% in the high redshift universe. So, so this is again, which means to say that the bar is forming from Z is equal to 7 gigayear and later, or the look back time is 7 gigayear or later. And later.
You have 5 minutes.
Yeah. So let me wait on. So yeah, one another case is our galactic center. So with TMT, when compared to Keck, you will have more number of stars to understand the galactic center, and the confusion limit is also reduced by an order of magnitude when compared to the Keck. So you will be able to get better estimates at the galactic center. Then a very interesting case is quenching. How are galaxies quenching? The passive galaxies fraction has increased at lower redshift when compared to the high redshift. So what is the reason? There could be several reasons or several modes of quenching. One is the environmental mode or the environment quenching, and the other is the other is internal, which means merger has increased the central concentration, and hence the mass has increased and it has gone into quench mode. So in the environmental quenching, there is triangulation, ground pressure stripping, and other things. So this is a plot of local group galaxies, where you see that people have studied the environmentally quenched fraction of satellite galaxies from stellar mass 8 to later. You see that the quenching fraction, or how much amount of the galaxies are quenched, you can see that it is only 30% of the galaxies are quenched in the local group system for stellar masses above 8 to 11. But now, if you there were some interesting estimates for local group satellite galaxies. If you see them below 10 to the 8 solar mass, it seems that all the galaxies below the 10 to the 8 solar mass have completely quenched. So there is this upturn which is seen in the local group systems. Is it very particular to the local group systems, or is it similar to all the cluster systems? Is one thing to understand. So these systems could be the ultra diffuse galaxies or ultra faint dwarfs, or some such systems. So total consensus of galaxies below 10 to the 8 solar mass is very important, and not only for local group galaxies, but for other galaxies as well. And TMT will be able to probe this, because it will be able to reach 26 to 28 magnitude per arc second square. The surface brightness of these galaxies could be of that time. So the traces for quenching could be totally different, like, or it could be multiple. H gamma versus D4000 is one way of checking quenching. It could be E plus A galaxies and the fraction of red sequence galaxies in the clusters. There could be star formation rates, kinematics, and stellar mass. So all these could be traces for quenching. So I stopped there. I just gave you a very little hint of what science the TMT can do. But I would like to now change topic and get into what is India's contribution towards 30-meter telescope. So so for the 30-meter telescope, India is providing segments. It's also providing the segment support assemblies, corresponding electronics, the edge sensors for sensing the differences between the two segments, adjacent segments, actuators which will correct for the variation of the segments, and the science instruments. We are doing several subsystems for WFOS, And of course, the major part is the software. We are giving more than 40% of the TMT software from India. So I would like you to listen to Sriram's talks for how the mirror segments from roundel is converted into a telescope-ready system. So I'm not going through this. So Sriram and team have been working on polishing the mirror. They have already got 2 mirror sets here in ITOF. I think you have all visited ITOF. So it's a very impressive system there. So TMT will also need a segment support assembly for every segment, and there are different 82 types of SSAs. So all the 580 SSAs which is required for the TMT is being made in India, and one of the first SSAs was assembled last year. After that, quickly they have also assembled the industry partners have also assembled 5 other SSAs. So actuators is it's a control system for the primary mirrors, and there are about 15-26 soft actuators that are required for TMT, and everything is being made in India. Sorry, I'm going in a quick way. The TMT edge sensors, which are required like 3,284 numbers. These are capacitive edge sensors. They are very precise systems. So these systems can measure up to 5 nanometer accuracy, and they are all made within India. So software, again, as I told you, the software for TMT architecture is basically the observatory software, the telescope control system, which I marked in red over here. Apart from that, WFOS and data management system are the main systems which are being made in India. And the kind of programs or the applications we are using are Scala, Java, and design. Coming to the science instruments, WFOS is one science instrument which India is heavily contributing. This is how the WFOS would look like on the national platform. We are giving a lot of spectrograph mechanisms. Apart from spectrograph mechanisms, here, which is the grating exchanger, the filter exchanger, the camera rotation system, we are also doing the calibration system. The entire electronics for the WFOS will go from India, and also the software, the instrument control software for WFOS will also go from India. So with this, I stop here, and thank you for your attention and patience.
Thank you, Ramya, for really winding up quickly. Just one picture question from
actually, I have a doubt about where you showed up to how much magnitude we can observe. In that slide, actually, you showed like for H band, we can go for like 8,000 resolution for a really high magnitude like 30. That I have doubt on, because for optical you have shown like up to 25 or something, you can go for 1,500 resolution. So I have doubt like H band, how can we go for higher resolution for such a high magnitude again? Like,
so H band is basically we are talking about iris, which is fed through AVO system. So I think we can reach fainter with that.
okay, it is like instrument basically because of instrument we can have better.
Okay, there is also lensing involved, which is going to enhance the light from the object. So that is also there.
Okay. Another like quick question is like, is there a coronagraph instrument in plan?
Yes. Actually, I didn't go into the details of this. So MODIS has a coronagraph. Can you confirm?
There is a plan. Yeah, that's the first slide.
Yeah, that is.
CSI would have.
Yeah, Michi would have.
Michi also would.
Michi, second generation will definitely have, but MODIS, I'm not sure.
Thank you.
Thank you, Ramya.
Long live India and France friendship.